Hello, today we'll discuss the full wave rectifier. In previous lecture, we have discussed the half wave rectifier, and in half wave rectifier, we have discussed that we get output which is unidirectional current, but the resulting current does not compare with the direct current that we would get from the battery. One reason is that in half wave rectifier, we are not making the use of other half of the supply voltage, means it is a half wave rectifier. That's why we are not getting the output for the other half of the supply voltage. But in full wave rectifier, uh, it is advantageous. We are using both half of the supply voltage, and it will rectify it, and we can obtain this through the full wave rectifier. So in this case, the arrangement is made in full wave rectifier that there is a supply voltage source which is connected to the center tap transformer. This is a center tap, secondary of the center tap transformer. This is a primary which is connected to the supply, and this is a secondary of the center tap transformer. One end is connected to the diode D1, and this is connected to the load resistance, and second terminal is connected to the common. This is center terminal of the secondary winding. Similarly, the P terminal is connected to the diode D2, and this is connected to here. So the supply voltage, we are applying the voltage like this, which is having the positive half cycle, and this is negative half cycle. But when this terminal A is positive and this B is negative, that means this A is at higher potential than C, and therefore diode D1 will conduct and the current will flow through the resistance like this, and this will complete the path, and we'll get the output like this. Now during the next half cycle of the supply voltage, what will happen? This will become positive terminal and this will become negative terminal. So at this time the diode D2 will conduct and current will flow like this, and this will again complete the path. So this is the use of both the half of the supply voltage. We are getting the output current through the load resistance for both half of the supply voltage. So we are getting the unidirectional current here. Therefore, let us, what is the supply voltage? VAC. The voltage across VAC is the V is equal to Vm sin omega t, and voltage across VBC, it is a minus V is equal to minus Vm sin omega t, and therefore the diode current 1, during the positive up cycle, the current will flow through the diode 1, therefore ID1 is equal to supply voltage by R, and therefore this Vm by R is nothing but I, and therefore this ID1 is equal to Im sin omega t. And during the positive up cycle, the diode D2 will not conduct, and therefore I2 will be 0. So this is for the positive up cycle. During the negative up cycle, what will happen? During the period that V is negative, diode 1 current, this will be now 0, because A is at the negative terminal of the supply and B is at the positive terminal of the supply. Therefore diode 1 will not conduct and diode 2 will conduct. Diode 2 current is equal to ID2 is equal to minus Vm by Vm sin omega t by R. So this Vm by R is nothing but Im. Therefore Im sin omega t. So this is the ID2 current. Now the at any instant the load current is given by at any instant the load current I is equal to the summation of id1 plus id2, and therefore this current will repeat itself twice every cycle of the supply voltage. Therefore the mean value of the load current is, now we have to find the mean and the RMS value. The mean value of the load current IDC is equal to 1 over pi, 1 over pi, because this is for the uh, one complete cycle. For half wave it was 1 by 2 pi, and this is a 0 to pi. Complete duration is for one cycle. Therefore Im into sine omega t into d omega t. Okay, so now we have to integrate this, we have to take this outside. Im, so Im by pi into integration of sine is cos omega t, limit is 0 to pi. Just put this Im by pi into minus pi is 180 degree, so it is 180 degree minus into minus of cos of 0 degree. So we have to put these values. Im by pi, cos of 180 degrees minus 1 and minus into this is a 1. Okay, so Im by pi, this is 1 plus 1, therefore this is equal to 2 Im by pi, and this is equal to IDC is equal to 2 Im by pi, means it is also equal to 0.637 Im. Now we have to find the RMS value of the load current. The RMS value of the load current is RMS value of load current is IRMS. IRMS is equal to square root of 1 by pi 0 to pi into Im square into sine square omega t into d omega t. Okay, so this is the RMS value of the load current, and we have to now take this outside. Im square by pi, and we have to write the formula for sine square omega t. It is a half into 1 minus cos omega t, okay, into d omega t. Okay, this is again we have to solve this further. Square root of Im square by pi, take this also outside, half, what will be there? So what is the integration of 1 with respect to d omega t? It is omega t minus integration of the cos omega t. It is a plus sine omega t, and this is the limit is 0 to pi. Okay, so we have to substitute here now. Im square by pi into half, it is a pi plus sine of pi into minus into 0 minus plus sign of 0. Okay, so again we have to solve this further. So what will be there? This is Im square by pi into half into pi sine 180. Sine 180 is again 0. Sine 180 is 0 minus 0 plus sine 0 is again 0. So this term, all term will be 0. What will be remain there? Uh, so it is Im square by pi into half into pi is there. So pi will get cancelled. What will remain? It will get cancelled. So it is Im square by 2 square root, and this is the Im by root 2, and therefore RMS value of the load current is Im by root 2. Okay, so this is the IDC and IRMS. Similarly, for the load voltage, we can similarly for load voltage we can write the mean value of load voltage, that is VDC, is equal to, again this is a 2 Vm by pi. Similarly, RMS value of the load voltage, RMS value of load voltage VRMS is equal to Vm by root 2. Okay, so for this circuit, again, if you find the efficiency, that is a power due to the DC component, that is a IDC square into R, power due to the AC component, that is a IRMS square into R. So what we will get here? We have to substitute this IDC. IDC is nothing but 2 Im by pi square into R. Here this is Im by root 2 square into R. This RR will get cancelled. The other terms will also, if you solve, you will get efficiency is equal to 8 by pi square, 8 by pi square, and if you find this, we will get since the for identical diode with a forward resistance RD is 0, the efficiency is equal to 0.81%. Since RD is equal to 0, that is a forward resistance RD is equal to 0, therefore we can write this is the, and therefore the waveform for the full wave rectifier is like this. This is the waveform we are getting. So this is the supply voltage for the positive up cycle. This is a supply voltage for the negative up cycle. Here it is a voltage as well as current on this side, and therefore for positive up cycle your current will be like this. Okay, and for the negative up cycle we are also getting the current like this. Output current is like this in the positive up cycle. In positive half cycle, current will be in the positive direction only, and for the negative half cycle, the current will be also in the positive direction. So this is the load current for every half cycle, and we are getting the output for both positive and negative half cycle of the supply voltage. That's why it is called as the full wave rectification. This is a full wave rectification. So this is a voltage V. This is the current flowing through this circuit. So in this way, we are getting the voltage across the, this will be the voltage across the diode. This is a time. So this is the waveform of the full wave rectifier circuit. So thank you very much for watching this video. Thanks.